Hi, welcome to my presentation on using Renyi-divergence and Arimoto-Renyi information to quantify membership information leakage. My name is Farhad, and I'm from the Department of Electrical and Electronic Engineering at the University of Melbourne. What today I'm going to talk about is membership inference. Most often in machine learning models, we have access to the data of a lot of data subjects, individuals, and we put that data in our favorite machine learning model training algorithm. And after training the model, we give other people access and interface to be able to query that model and gain an insight about the data. Now, when an adversary comes and query the model to figure out if individual X and Y was in the training data set or not, we call that membership inference attack. So the adversary has the data of an individual in their mind. They come and query the model, get a Y hat, which is the label or the output of this machine learning model. And then based on the data that they got, X and Y, and the output of the machine learning model, Y hat, they're trying to figure out if this X and Y is in the training data set or not. Most often, they have a black box access to the model, so they don't know the weights in the model, but they would know the output of the model. Now, membership inference attack matters when the data itself doesn't possess any significance in terms of privacy, but knowing that the data is part of that training data set might possess some kind of privacy concerns. For instance, you can think of a startup company having the data of its customers and then training a machine learning model based on that data. And then you don't want banks that would have access to the data of their people. For instance, they know the transaction information, they know the salary, they know the location they live, and all the other information to be able to figure out if an individual was a customer of that startup company or not. That's particularly concern for the startup company because they want to keep the data hidden because that's part of the business model and that's what they're trying to sell access to the data. So they want other people to get it for free. Now, adversarial attacks are easy to construct. There is a lot of example of them out there in the computer science literature, and they actually work in practice. So that's why we are focusing on this category of membership inference attacks in this paper. Now, to be able to understand membership inference attacks, we are looking at this cryptographic distinguishability game. We think of a setup that an adversary finds in data X and Y and gives it to the challenger. You can think of the challengers in nature, if you're more familiar with the game theory framework. And then the challenger flips a coin. If it comes head, then it would put this X and Y in the training data set. And if it comes tail, then it doesn't put it in the training data set. It populates the rest of the training data sets and train the machine learning model, and then computes the output of the machine learning model on the data X that the adversary provided, and it gives its Y hat, which is the output of the machine learning model. And then based on this information, X, Y, and Y hats, the adversary wants to estimate M. What's the flip of a coin, head or tail. And the success of it would be determined by the challenger. So the adversary's performance is given by this probability of not being successful. So if this probability is very small, then the adversary is very good in doing its membership inference attack. If the probability is very large, then it wouldn't be that good. And we go for this cryptographic distinguishability framework, particularly to avoid having a knowledge on the prior on M. If you didn't have this framework, then the nature would be taking over the challenger, and the flip of a coin would be the nature's way of saying that if this X and Y is part of the training data set or not. Now, everything would be the same as this framework, except that you have to deal with the priors on the M. And that would make the job a bit more complex. So that's why we are not, going for that framework. But, whatever I'm saying here would still work with just, with some constants being different in that framework as well. So one way of, measuring this privacy loss in the membership is using the alpha divergence, using the Renyi-divergence of order alpha to be able to compare, the effect of M being 0 and 1 on the output, which is we only have access to the distribution of the Y hat. So we want to see M being part of the training, the X and Y being part of the training data set, i.e. M is 1, or X and Y not being part of the data set, M is 0, how much it changed the distribution of the Y hat. And the difference in that distributions would let the adversary be able to figure out was M part of the training data set or not. So for the case of alpha equal to 1, this measure has been used previously by us to trying to, understand a little bit membership inference attacks. And the case of alpha being infinity, some other people have used these measures in the past to be able to, say, the effect of the, what's the effect of the membership inference, effect of various factors on the membership inference attacks. Another way of, capturing membership privacy loss is to use information I alpha, which is the Arimoto-Renyi information of order alpha, of the amount of information that's available about M in Y and Y hat. And again, this measure has been used in the past for the alpha equal to 1 by us to be able to investigate, membership inference. Now, why these measures of information make sense? One is because of this upper bound. The probability of adversary being not successful, and adversary wants to select his best policy, so there is an infimum here, is upper bounded by this term, which is a decreasing function of gamma. Note that this alpha minus 1 is negative because we are only looking at the alpha between 0 and 1. So this function is decreasing in gamma. So when gamma gets larger and larger, this upper bound gets smaller. So it becomes easier for the adversary, the optimal adversary, to distinguish m's, m being 1 or m being 0. So we want, from the perspective of us, not the adversary, this gamma to be small, so that make the job of the adversary harder and harder. Now we would have this other inequality, a lower bound again than this probability of error, the best case probability of error in terms of the perspective of the adversary, the best adversary. And this lower bound is such that when the amount of information gets smaller and smaller, the lower bound becomes larger. So having a small amount of information, intuitively makes it hard for the adversary to be able to distinguish, m was 0 or m was 1. So small information, small success on behalf of the adversary. Large information makes it easier for the adversary. So both these measures are such that when they are small, the job of the adversary is hard, and when they are large, the job of the adversary is easier. So they kind of intuitively make sense for us to select them as, measures of information leakage. Now, these two measures are, quite related to each other. You often don't need to study both of them, finding a bound on one or the other is, providing a nice bound on the other one as well. So you would have this relationship between, C1 and gamma 1. And knowing that, that gamma is a non-decreasing function of alpha and C is a monotonically increasing function of the alpha, you would have these extra relationships on gamma alpha and C1 over alpha. So finding an upper bound for gamma would give an upper bound for this one, and finding a lower one for this one would give a lower one for gamma. So, it's always, it's sufficient to look at one of them. In addition, they satisfy a very nice important property that post-processing the output of the machine learning model, so if we were to do additional processing shown by this P, would not increase the amount of leaked information, can only decrease the amount of the leaked information. Post-processing is good for reducing membership inference. Membership inference leakage. And that's something that, makes quite a bit of sense. Post-processing would not increase information, so we would have this bound, and post-processing would make that, divergence smaller as well. Now, a very important part is to figure out, where do these measures of information sit with respect to the existing literature and the amount of, the membership on the information leakage. A very important measure of information leakage is the maximal leakage. It's a guessing-based, sorry, this should be axiomatic, a guessing-based measure of information leakage that, lets the adversary guess the value of the private information, and you look at the probability of the success of the adversary. And maximal here is because, you look at every possible guess. You don't look at, guessing a specific, attribute. You look at, all the possible attributes that might be able to guess. Now, this measure has been extended to provide a tunable measure of information leakage. An example of that, tunable measure of information leakage in this paper is alpha leakage. And the alpha leakage, shows you how much information is leaked from, this here in this example, Y and M, from M to this Y and M, and this is identical to our definition of C, because they show that the alpha leakage is equal to the Arimoto information, and here we are using the Arimoto information for computing this membership inference information leakage. So we would have this identity, and then as a corollary, we get that this C is a quasi-convex function of this conditional distribution, which is very nice, because if we were to optimize, if we were to minimize the amount of the leaked information by changing this conditional distribution, we might be able to construct a numerically efficient problem to solve, depending on what kind of measures do we use for the utilities that measure convex or not, and the size of decision space. So because we are dealing with discrete variables, there is quite a lot of them, and if you're looking at a small alphabet sizes, then this problem could be potentially numerically efficient to solve. A very important method for countering the effect of membership inference in the literature is differential privacy. Differential privacy has been used quite a lot in the computer science literature, and has been proposed as a successful measure for countering the effect of membership inference. Now, to be able to formally define differential privacy, we are going to look at the training algorithm A as a stochastic mapping from the training data set to the machine learning model. Now, why stochastic? Because most often when we want to ensure differential privacy, we use something like stochastic gradient, some kind of randomization in the output. So then your machine learning model would be possibly random. And the neighboring data sets D and D prime, show the data sets that only differ in one entry. So everything else is constant. And that makes sense for us, because in two membrane data sets would be having the data of an individual and not having the data of an individual. So we want to, when you want to do the membership inference, you want to figure out if that, the data of a certain individual was part of the data set or wasn't part of the data set. So it was in D or not, which would be the D prime case. Now, differential privacy, probably a lot of people would know about them, but let's a refresher. You would say that, this training algorithm, which is stochastic, is differentially private with parameters epsilon and delta. If the output, probability of observing an output is upper bounded for the case of D prime, the data set, that differs in one entry with D, by, exponential of epsilon times the probability of observing the same kind of outputs for the case that we are using D plus delta. So when delta and epsilon are very small, these probabilities of observing an output would stay the same, irrespective of if we are dealing with D or D prime. So we would not be able to use the outputs of the algorithm to reverse engineer and figure out if we are dealing with D or D prime. So if our entry was part of the data set or not. So in this case, you can show nice upper bounds on the amount of the leaked information. If you go for pure differential privacy, so when the case is delta is equal to 0, then the amount of the leaked information is upper bounded by this term here. So this term is a increasing function of epsilon. So as epsilon gets larger and larger, this upper bound grows larger and larger. And for the case that epsilon is 0, the upper bound is 0 too. And we know that there is a lower bound, this gamma is greater than or equal to 0. So if we know that for the case of epsilon 0, this gamma, or the amount of leaked information for an individual, is equal to 0. So if you go for epsilon 0, there is no leakage, but epsilon 0 would have very bad, very bad utility. So in that case, you would not be able to say much. Your machine learning model would not be that good. So you would want to be able to trade off selecting a larger epsilon when leaking a bit of information to be able to get some form of utility. Now, for the case that we don't go for the pure differential privacy, we go for epsilon delta differential privacy, this upper bound changes. Not that this alpha minus 1 is negative, because we are dealing with alphas between 0 and 1. So this upper bound makes sense. And again, this is an increasing function of epsilon, an increasing function of delta. So when delta is larger and epsilon is larger, there is more leakage. I mean, there's a larger upper bound. So potentially there is more leakage. And for epsilon equal to 0 and delta limiting towards 0, there is 0 information leakage. And again, that's the case that you don't have any utility. So you won't want to be able to trade off some utility by selecting the epsilon and delta a bit larger than 0. And let's draw this, for the case of alpha equal half. And for the case of pure differential privacy, you end up with this curve that rapidly goes, larger and larger. So this bound kind of only works for very small epsilons. And for a small epsilons, you can see the amount of leakage is fairly limited. In this band, for the case of epsilon and delta differential privacy, you can see that, the effect of delta is very pronounced. For selecting an epsilon, for instance, 10 to the power of -2, then the effect of the delta is very easily seen here that, by increasing delta, the amount of leaked information increases as well. Now, when epsilon goes to 0 and delta goes to 0, the amount of leaked information goes to 0 as well. To conclude the work, in this paper, we just wanted to, set the scene, construct, a framework for understanding membership inference. We wanted to use hypothesis testing, which is a very natural fit here. We are doing a binary hypothesis testing here to be able to figure out, if the data is in the training data set or not. And based on that view, we defined a couple of measures of information leakage. We use these measures of information leakage to understand, some stuff about, membership inference attacks. We used this membership inference leakages to be able to understand the effect of differential privacy, to be able to, set the value of, epsilon and delta to get a certain level of, membership inference privacy, and then, trying to see what's the effect of that on the utility, and then try to balance the utility and privacy, using these bounds. We also, studied the, properties of these measures of information. One of them was a measure that has been used, quite frequently in the privacy literature, the alpha leakage. And based on that, we could, get very nice properties about this measure of information leakage in the case of membership inference privacy. The quasi-convex nature of that measure is very helpful when you're, trying to cast an optimization problem to minimize the amount of leaked information. Now, a very interesting avenue for future work is to understand the effect of issues like fairness, overfitting, and memorization on membership inference attacks. Why these matter? Because a lot of, experimental papers in the computer science have looked into, what will happen if we have overfitting, and showed that, overfitting is very bad in membership inference. And why is that? Because, the output of the machine learning model is often much more confident when you have overfitting on the data that you have in the training data set in comparison to the data that you would have in the test data sets. So you can use this confidence to be able to see that the data was part of the training data set or not. Memorization is even worse because parameters in the deep learning model are selected such that they memorize even the data. So you would be able to reverse engineer a trained machine learning model to be able to figure out what was the training data set. Now recently there have been fairness has been pointed out as an issue in the membership inference too, because most often if you want to achieve fairness, you have to manipulate your training algorithm, or you have to manipulate the output of a machine learning model to be able to have a certain sense of fairness, and that manipulation results in a lot of information leakage. So that's what you want to avoid. So these are very interesting things to be able to investigate theoretically using these measures of information leakage that we define in this paper. And with that, I would like to conclude my paper and say, you can reach more information on my webpage, or you can, communicate with me on this email address or on Twitter if you have any questions and you would like to know more about, what we're doing these days on this topic. And thank you very much for your time and watching this video.